Welcome to Black Hole Basics, where we unravel the deepest mysteries of the cosmos, starting with the fabric of reality itself. When you look up at the night sky, you see stars scattered across space, but you are also looking back in time. We intuitively feel that space is a stage where things happen, and time is a clock that ticks forward for everyone. For centuries, this was the accepted view, where space was a rigid container and time flowed at the exact same rate. Isaac Newton championed this idea, believing that 1 second on Earth was exactly equal to 1 second anywhere in the universe. In this classical view, time is absolute, a universal master clock that never changes, regardless of where you are or move. This makes sense in our daily lives because we move much slower than the speed limit of the universe, light itself. However, in the late 19th century, physicists discovered something strange about light that would shatter our understanding of reality forever. James Clerk Maxwell found that the speed of light is a constant number, regardless of how fast the observer is moving. Imagine running forward on a train. Your speed adds to the train's speed, but light does not behave this way at all. A young Albert Einstein realized that if the speed of light is constant, then space and time themselves must be flexible. He proposed that to keep light speed constant, time must slow down for moving objects, a phenomenon called time dilation. Simultaneously, space itself must shrink in the direction of motion, meaning distances are not absolute but depend on your speed. Einstein merged the 3 dimensions of space and the 1 dimension of time into a single 4-dimensional fabric called spacetime. Space and time are no longer separate entities. They are interwoven threads of the same cosmic tapestry that pervades the universe. Physicists visualize this using light cones, mapping out all possible paths an object can take through this 4-dimensional spacetime environment. Your entire life, from birth to death, creates a permanent tube through this 4-dimensional block, known scientifically as a world line. This leads to the block universe theory, suggesting that the past, present, and future all exist simultaneously in this structure. We only experience the now as a moving slice through this block, but physically, the future is as real as the past. Different observers moving at different speeds cut this block at different angles, meaning they disagree on what is happening right now. This is the relativity of simultaneity. 2 events can happen at the same time for you, but at different times for others. But Einstein did not stop there. He realized that this fabric of spacetime is not just a stage, it is dynamic. Massive objects like stars and planets bend and curve the spacetime around them, creating what we perceive as the force of gravity. Gravity is not a mysterious force pulling you down. It is the result of you sliding along the curvature of spacetime. Matter tells spacetime how to curve, and spacetime tells matter how to move. This is the essence of general relativity. Even light itself must follow these curves, meaning gravity can bend light beams, acting like a giant cosmic lens in space. This was famously proven during a solar eclipse in 1919, confirming that space is indeed curved by the mass of the sun. This isn't just theory. Without accounting for spacetime curvature, the GPS in your smartphone would drift by kilometers every single day. Time flows faster for satellites because they are farther from Earth's mass, experiencing less curvature than we do on the surface. Technically, your head ages slightly faster than your feet because gravity is weaker the higher up you go from the ground. The most extreme example of curved spacetime is a black hole, where a massive amount of matter is packed into zero space. Here, the curvature is so intense that space falls inward faster than the speed of light, trapping everything including light itself. If you could hover near a black hole, you would see the universe outside aging rapidly while your own watch ticks normally. At the center lies the singularity, a point where spacetime curvature becomes infinite and our current laws of physics completely break down. When black holes collide, they send ripples through the fabric of spacetime, known as gravitational waves, which we can detect on Earth. These waves literally stretch and squeeze the space you occupy, proving that spacetime is a physical substance that can vibrate. Spacetime is also expanding, carrying galaxies apart from each other like dots on the surface of a balloon being inflated. It is not that galaxies are flying through space, but that the space between them is being created and stretched constantly. A mysterious force called dark energy is accelerating this expansion, stretching spacetime faster and faster as the universe gets older. But what happens if we zoom in on spacetime to the smallest possible scales, far smaller than atoms or protons? Here, the smooth fabric of Einstein's spacetime breaks down into a chaotic, boiling mess known as quantum foam. This reveals the biggest conflict in physics. General relativity works for the big, but clashes with quantum mechanics for the small. Theories like string theory attempt to reconcile this by suggesting spacetime has hidden extra dimensions curled up too small to see. Imagine an ant on a wire. From afar, it looks like a line, but up close, it is a curled dimension. These hidden dimensions could explain why gravity is so weak compared to other forces, as it leaks into other dimensions. Another fascinating prediction of spacetime geometry is the wormhole, a theoretical bridge connecting two distant points in the universe. Instantly, by folding the fabric of spacetime, a wormhole could allow travel between galaxies faster than light, without breaking physics rules. However, keeping a wormhole open would require exotic matter with negative energy, something we have yet to discover or create. Closed time-like curves are loops in spacetime that theoretically allow time travel, returning to the past to meet your former self. This creates paradoxes, like the grandfather paradox, suggesting that the universe might prevent such loops to protect the timeline's integrity. Stephen Hawking proposed the chronology protection conjecture, believing the laws of physics conspire to prevent time travel on macroscopic scales. This means that from light's perspective, the universe is timeless, an instant connection between the source and the destination. This means that from light's perspective, the universe is timeless, an instant connection between the source and the destination. Some physicists even argue that spacetime might not be fundamental, but emerges from quantum entanglement, like pixels on a screen. This idea, called it from qubit, suggests that the geometry of spacetime is stitched together by quantum information and entanglement. The holographic principle suggests our 3D reality might be a projection of information stored on a distant 2D surface. If true, then spacetime is just a user interface for a deeper, more abstract reality made of pure quantum information. So, is time real, or is it just an illusion created by our brains to make sense of the entropy? The arrow of time is driven by entropy, the tendency of the universe to move from order to disorder and chaos. Spacetime began at the Big Bang, meaning asking what happened before is like asking what is north of the North Pole. And it may end in a heat death, where time loses its meaning because nothing ever changes or happens anymore. We have journeyed from Newton's rigid stage to Einstein's flexible fabric, seeing how mass, energy, and motion sculpt our reality. Right now, you are traveling through time at the speed of light, simply by sitting still and existing in space. You are also bending spacetime with your own mass, pulling the Earth slightly towards you, just as it pulls you. Understanding spacetime connects us to the cosmos, realizing we are not just inhabitants of the universe, but part of its fabric. The quest to fully understand spacetime continues, as physicists hunt for the elusive theory of quantum gravity at particle colliders. Every answer we find opens up 10 new questions, proving that the universe is far more creative than we imagine. Perhaps one day, we will master spacetime navigation, allowing us to reach the stars that currently seem forever out of reach. Until then, we are travelers on this spaceship Earth, drifting through the curved geometry of the solar system's gravity well. Concepts like time flowing backwards or parallel universes remain in science fiction for now, but the math does not forbid them. Quantum mechanics suggests multiple timelines might exist, splitting every time a decision is made or a particle interacts. In the multiverse theory, spacetime is just one bubble among an infinite ocean of other bubbles with different physical laws. The beauty of spacetime is that it frames our existence. Without space, we have no place. Without time, we have no life. Einstein's legacy teaches us to question the obvious, to look beyond common sense, and to trust the language of mathematics. Even simple motions like swinging on a playground involve complex interplay of potential energy, kinetic energy, and curved spacetime paths. We perceive the rotation of the Earth as the passage of days, a rhythmic cycle embedded in our biological clocks. Biology itself is a fight against the ravages of time, utilizing energy to maintain order within our bodies temporarily. We build monuments like pyramids to extend our influence through time, leaving a mark on the spacetime block for the future. Our radio signals are expanding spheres in spacetime, carrying our music and voices to star systems light years away from us. Because of the light speed limit, any aliens receiving our signals today are hearing news from decades or even centuries ago. Telescopes like James Webb are time machines, allowing us to see galaxies as they were billions of years in the past. We are looking at the ghostly images of the infant universe, light that has traveled across expanding spacetime for eons. Gravity pulled dust and gas together to form our solar system, creating a local pocket of order in the chaotic universe. The history of our planet is just a tiny layer in the massive block of spacetime that constitutes the universe. Events like the asteroid impact are fixed points in spacetime, unchangeable events that steered the course of evolution toward us. Now, we dominate this planet, but our time here is a blink of an eye compared to the cosmic calendar. We must use our time wisely, as we face challenges that could shorten our civilization's journey through this spacetime fabric. Our future likely lies beyond Earth, expanding our presence to other planets, and eventually to other stars in the galaxy. If we can master the physics of spacetime, we might one day build warp drives to bypass the cosmic speed limit. Future generations might look back at us as the ancestors who first dared to understand the true nature of reality. But for now, many mysteries remain locked away, waiting for the next Einstein to unlock the secrets of the universe. That person could be watching this video right now, inspired to dig deeper into the mathematics of space and time. The study of spacetime is not just for physicists, it changes how we all perceive our place in the universe. It teaches us to cherish the present moment, the only slice of the block universe that we can truly experience. Like a river flowing into the sea, our individual timelines merge into the vast, interconnected ocean of cosmic history. We draw lines between stars to make constellations, finding patterns and meaning in the chaotic arrangement of the cosmos. The cosmic web itself is built upon the scaffold of spacetime, guiding the formation of galaxies along invisible gravitational filaments. The resemblance between the cosmic web and our neural networks hints at a deep, recursive symmetry in nature's design. Just as atoms are mostly empty space, the universe is mostly empty, yet it is full of fields and potential. There is no such thing as truly empty space. It is alive with fluctuating fields that give rise to matter. We are essentially excitations of these fields, temporary waves traveling through the eternal ocean of spacetime and quantum energy. When we die, the atoms that make us up return to the cosmos, continuing their journey through space and time. Just like stars, we are part of a cycle of recycling matter and energy that has lasted for billions of years. This perspective should make us feel small, but also incredibly lucky to be conscious observers of this magnificent reality. We are the universe experiencing itself, a way for the cosmos to know its own vastness and its own history. From the warping of gravity to the dilation of time, the story of spacetime is the story of everything. It is a story that is still being written, with chapters on dark matter and quantum gravity yet to be finished. What aspect of spacetime blows your mind the most? Let us know in the comments below. We love reading your theories. If you enjoyed this deep dive, make sure to subscribe and hit the bell icon so you never miss an update. Check out these other videos on the screen to continue exploring the strange and wonderful laws of our universe. Your support helps us create more content like this, bringing complex physics down to earth for everyone to understand. Remember, reality is often stranger than fiction, and the truth is out there, waiting for us to find it. Thank you for watching Black Hole Basics. Keep looking up, keep questioning, and join us next time for another cosmic journey.